Hello, everyone. Welcome to session 6. We are going to start very soon. Hope everybody had a lovely lunch. By the way, the first speaker, she's here? Okay, great, excellent. Thank you very much. So, okay, the section 6 is architecturing the security or security for architectures. So hope everybody will enjoy this section. And I'm the session chair, Mei, who is from the IBM research. Currently, it's a research staff member working on cloud infrastructure. And so first paper is actually a best paper nominee in these, the host 2023. And so the presenter, Nadja Ramhöj Holtryd, received a master's degree in computer systems and networks and PhD degree in computer architecture from Chalmers University of Technology, Gothenburg, Sweden in 2013 and 2023 respectively. She required 3 years of industrial experiments working as system developer at Swedish tax agency 2014 and 2015, and embedded software developer at Volvo GTT Sweden 2015 to 2016. She is currently system architect at 0 Point Technologies, Gothenburg. Her professional interests include performance and security of memory systems. So let's welcome our speaker for the first paper of the presentation.
Thank you for the introduction. My name is Nadja Ramhöj, and I will be presenting SCALE, Secure and Scalable Cache Partitioning, a work I've done in collaboration with Madhavan, Manivannan, and Stenström. Modern multi-core architectures use a tile architecture, where each tile consists of a core, per-core caches, and part of the shared cache. This shared cache can provide fast access to a limited set of data to avoid the slow access to the main memory. As has been discussed also yesterday, there are attacks that can exploit this timing variability. And these attacks can leak cryptographic keys and user data and poses a severe security threat to the system. Here is a simplified view of the multi-core, where we only have 2 cores, each executing the victim and adversary process, which is the threat model we consider in this work. They share the cache where the actions by the adversary will impact the victim, and the adversary can therefore extract information. Static partitioning can provide protection since it can isolate the data belonging to the 2 different processes from each other. However, it leads to lower performance since it leads to a worse utilization of the cache space. A cache partitioning solution consists of 2 parts: an allocation policy that decides the size of the partitions, and an enforcement mechanism which maintains these partitions. A static cache partitioning solution only makes one decision, while a dynamic policy first collects the cache requirements of all the co-executing applications and then decides on allocations that will be used for the next time period, and then again detects the new cache requirements and updates the allocations. However, dynamic partitioning leaks information even in the presence of a secure enforcement mechanism, and I will show how next. Here we again have the adversary and victim process executing on different cores, and they share a dynamically partitioned cache with only 4 slots of data for simplicity. The victim performs a sensitive calculation, which depends on the value of the secret key. The adversary starts by setting the cache allocation to a known initial value, in this case equal. Then it waits for the victim to execute. In the first case, the victim performs calculation A, since it has the key value of 1, which has a cache requirement of 3 slots. This is then detected by the dynamic allocation policy, which updates the allocation to 3 slots for the victim application. In the second case, the key value is 0, leading to a cache requirement of only 2 slots, leading to no update to the dynamic allocation. Now, the adversary can, by accessing its own data, time these accesses and determine that there is a difference in the 2 cases, where in the first case, where some of its data has been evicted from the cache, it will have a longer access time, leading to that it can infer the value of the secret key. Prior work has used 2 different strategies. The first work, SecDCP, does not consider the cache demand of sensitive applications, which in the previous example will lead to the same allocation regardless of the value of the key and the same timing. The second strategy is used by Optimus, which only reconfigures once for each application, and then hopefully not close to any sensitive computation. The limitations of both of these prior works is that they do not improve performance over an unpartitioned shared cache, since they do not adapt to the different applications' cache requirements. The problem we want to address is how to provide both protection against timing-based side-channel attacks and to provide a performance benefit of dynamic partitioning. So we make the following contributions. We demonstrate conflict and occupancy-based attacks on the cache allocation policy side channel, and we propose a framework for characterizing this side channel by the channel bandwidth and error rate. We propose Scale, a solution for secure and scalable dynamic cache partitioning, which has information theoretic security guarantees. And the key ID we use in Scale is to use randomization in 3 different ways to meet the requirements. The Scale solution works as follows. We start by collecting the cache requirements of all the co-executing applications, and we then use a non-secure dynamic allocation policy to decide on the best allocations. In our paper, we use the algorithm look-ahead. These non-secure allocations are then secured, first by adding noise to the allocations, then by randomizing and affecting the change rate of the allocations, and thirdly, by changing the reconfiguration period. The 2 second defenses are needed in order to address occupancy-based attacks, where it is important to also protect against repeated patterns in the allocations. This leads to secure allocations that can be maintained by our secure enforcement mechanism. I will now provide the intuition for the 3 defenses by a simplified example. So if we'll have the same example as before with a calculation with a key value of 0. With noise, we change the allocation, adding 1. This leads to the longer timing being observed by the adversary and leads to that it will see the wrong key value. The second defense affects the change rate, which will not allow the cache allocation to change as before. So in the interfere step with change rate, now the allocation, if we have previously calculated with a key value of 1, it does not change to 2 ways. And the same thing happens when we make the calculation with the key value of 0, which actually has the cache demand of only 2 slots. Now again, we can get the wrong timing and infer the wrong secret. The third defense, which randomizes the reconfiguration period, works as follows: that here we have made a calculation with a key value of 1, and now currently we're calculating with a key value of 0. But the cache demand we see at this point will be influenced by the previous key calculation. So again, the wrong timing is seen by the adversary, leading to the wrong key value. We provide more details in the paper about the three defenses. So the security guarantees we provide for Scale is based on differential privacy, where the goal of differential privacy is to be able to release useful statistical information about the population while not leaking individuals' data. And this is done by adding noise using a mathematical framework. As an example, if we have two data sets, A and A plus X, and then we add noise, which is drawn from the Laplace distribution, where this plot shows on the y-axis, we have the probability of obtaining a certain noise value. On the x-axis, we have the range of different noise values. Now we will get two different output distributions, and the difference between those two will be at most epsilon, which the guarantee provided by differential privacy, which will hinder the adversary from knowing the value of x. In Scale, the two data sets are allocations at different time periods. And using differential privacy, we can provide quantifiable and information-theoretic security guarantees. Scale is also configurable, where the system administrator can provide security requirements per application in the form of epsilon, and the largest protected range, which is the largest change in allocation in cache demand. So in the previous example, this is the difference in cache requirement between performing calculation A and calculation B. This determines the correct amount of noise to add to this application. Further, we observe that cryptographic libraries typically have small working set sizes, which leads to a small protected range. And our results show that this leads to a small performance cost of adding noise. We make a sensitivity analysis of the size of the protected range, and for large protected ranges above 512 kilobytes, it's more beneficial to instead use static partitioning. The Scale enforcement mechanism is based upon the non-secure delta enforcement mechanism. Let's follow a load to get an intuition behind how it works. So we first calculate a hash based on the 8 bits following the set index and use this as an index into the cache bank table, where there is one cache bank table per unique domain ID. This provides which bank the data is located in. Now we go to bank 1 and look up where the data is located. And we find that it's located in way 0 to 7. This two-level design of combining bank and way level partitioning provides a scalable design and the possibility of placing data in a locality-aware manner. So some results. We simulate using the Sniper simulator multi-program workloads using the Spec 2006 benchmark suite. And the metric we use for performance is normalized weighted speed up over baseline, where baseline has a shared cache without partitioning. A dynamic partitioning solution with non-secure allocation policy and enforcement mechanism provides 21% performance improvement, while prior work does not improve performance over baseline. SecDCP Scale provides a 14% performance improvement, and for a mix of applications with and without security requirements, it can close the gap to the non-secure dynamic partitioning solution. To summarize, cache-side channels poses a severe security threat to the system, and partitioning can provide a solution. With Scale, we leverage randomization to address both conflict-based and observation-based attacks. And it can provide quantifiable security guarantees based on differential privacy. It provides a 14% performance benefit over a shared cache and outperforms state-of-the-art. Thank you.
Any questions from the audience?
All right, this is Harvest from Villanova University. Just a quick question.
Yes.
The proposed scale, do you have any practical application validation?
What do you mean with
You know,
practical?
for example, say you have like 14% of a shared cache. Have you done any like a practical processor or whatever testing? Or it's just a theoretical simulation?
I mean, this is the performance numbers from dynamic partitioning, which is where the performance comes from. I mean, that has been evaluated in a number of different papers. We also evaluate, instead of having this fine-grained locality where partitioning, we also compare against applying scale to something similar to Int'l cat, which just do non-locality where partitioning, and yeah, it provides a performance improvement also in that case.
Okay, thank you.
Yeah.
A question that I think was related to this one. There's a certain workload dependence, presumably to the improvement. Did you look at what kinds of workloads get more or less benefit from your method?
Yes, an excellent question. Yeah, I mean, we used 21 randomized workloads from the Spec 2006 benchmark suite, but I mean, it's always dependent on if the application is sensitive to the cache size. So, I mean, for workloads where all the applications are insensitive to the last level cache, there's no performance improvement at all. So it's all dependent on the if it is sensitive to the cache requirements.
Makes sense. Thank you.
Yeah. Any more questions?
Okay, great. Let's thank our speaker. Thank you so much for the great presentation. Thanks so much. For the second paper, the presenter is Lilian Bossuet. Is a professor at the Jean-Baptiste University of Saint-Étienne in France. He is head of the Secured Embedded Systems and Hardware Architecture group of this university. His main research focus is the hardware security of embedded system and SoC. He has published over 200 referred publications in these areas and is a senior member of the IEEE. Let's welcome our speaker. Thank you very much.
So thank you for this introduction. It's my great pleasure to be here today to present you this work about the way to establish a covert channel in modern system on chips. So the first thing is perhaps to remind you what is exactly a covert channel. So in this case, the aim of the covert channels is to perform communications, hidden communications between two malicious entities. So this malicious entity could be software application or hardware IP. But in fact, it's not possible to have a direct communication by using the usual way to communicate, for example, the Axibus in these system on chips. Because of software isolations, if we use some security rules provided, for example, by Trust Zone, the technology, the ARM technology, to secure the software part of the SOC, or also if there are some logical or physical isolation between the malicious entity. So this malicious entity will try to use physical channels to send the information from one part to another part. Typically, in this case, in the case of system on chips, it is possible to use the following physical channels: the supply voltage, the clock frequency, or the cache memory access time. So this talk is linked to the second keynote of this morning's, because we would like to maliciously manipulate the clock frequency to send information inside the system on chips. For this work, the target is Xilinx UltraScale Plus system and chips because it is a typical case of modern and heterogeneous system and chips. So we can see on this figure that it's really complex architectures with two main parts. In blue, the processing systems that embed many different cores, and in yellow, the programmable logic that is in fact the FPGA part of the SoC. And there are many other things in this chips. But what we want in this work is to try to establish communications between one on the processing unit. So on the left on these figures, but there are two different processing units, so application processing unit that embed several Cortex i53 core, and the real-time processing units that embed the Cortex R5 core. So we would like to perform the communication between one of these processing unit and the FPGA part of the SoC. So the next figures, yes, is more same to understand. So in fact, for the power domain point of view, the architecture is split in three parts. On the left, the lower power domain is dedicated to the Cortex R5 processor. And in the middle, the full power domain is used for the Cortex A53, and on the right, one power domain is dedicated to the FPGAs. So we can see that in fact, all these different power domains use different clock, but all the clock are in fact linked to the reference clocks, and several PLLs allow the designers to provide or to manage the clock frequency of the power domains by using divider factors to tune precisely the clock frequency of each part. So we want to change the divider factor used to generate the clock frequency of the FPGAs in order to send the information from the processing unit to the FPGA. So what we have to do is to be able to perform the measurement of the clock frequency inside the FPGAs. So to do it, we use this ring oscillator based sensor. So this kind of sensor have been already presented in the case of remote side channel analysis. So it's really a simple sensor with a very small ring oscillators following by the digital counters. And so we use in parallels many sensors to be able to have a precise measurement of the clock frequencies. On this figure, we can see the output of the sensor for different frequency used for the clock of the FPGAs. So the variability of the measurement equally different from one frequency to another. It depends, in fact, on the tuning of the digital counter. But what we want to use the frequency that provides the measurement with the lowest variability as possible. So we can select these three frequencies, 300 megahertz, 150, and 100, because the variability is really low, and moreover, it is really easy to distinguish one frequency from another frequency by using a tracer, for example. The second thing to do is to be able to characterize the Covert-Channels to estimate the transmission rate of the communication. So in the paper, you can find all the detail of this characterization. But for example, we perform the dynamic characterization of the PLLs to know, for example, the time required for a transition to go from one frequency to another frequency. So for example, from 150 to 100 megahertz, the PLL need around 600 nanoseconds to change the frequency, and something close, a bit slower for the transition from 100 to 150 megahertz. So now how to perform the communications. So in the paper we present several ways to establish the covert channel. So I'm going to present you three possibilities. So the first one is the possibility to establish the covert channel between the real-time processing unit and the programmable logic. So in this case, it is bare metal applications systems. So the software applications has to write directly in the register using for controlling the divider factors of the FPGA clock frequency, the adequate value of the dividers to select one frequency. Inside the FPGA, the arrow-based sensor performs the measurement of the frequency. So now, how to make the modulations of the information. So in this case, we use a tree frequency. We use 100 megahertz for the symbol 1 frequency transmissions, 300 megahertz for the symbol 0 frequency transmissions, and 150 megahertz for the inter-symbol frequency. So you can see the output of the sensors that you can obtain if you send alternatively a 1 and a 0. So with these covert channels, we can achieve a higher transmission rate of 273 kilobits per second. So it is a good transmission rate to transmit quickly high number of informations. The second possibility, second covert channels, is the same thing, but from the APU to the FPGAs. In this case, it is a case of a Linux application system. So the software application has to use IPA and dedicated drivers to specify directly the frequency of the FPGAs. So it is lower to perform this module. In fact, the impact on the clock frequency need more times for a modification of the frequency. So we use only, in this case, 2 frequencies, and you select the frequency for which the PLL have the faster behavior. So we select the frequency 150 megahertz for the symbol frequency transmissions, and 300 megahertz for the inter-symbol frequency transmissions. But in this case, the time for the transmission of the symbol 0 and symbol 1 is not the same to be able to make the difference between transmission of the 0 and 1. So with these systems, the transmission rate is clearly lower, so it is a bit more than 1 kilobit per second. But in fact, it's not really an issue, because in most of the case, when you perform a covert channel communications, it is not to transfer a lot of informations. If you want to, for example, communicate a secret key of symmetric ciphers, it is not a big number of bits, 100 or a bit more. So even with the transmission rate, it could be interesting to use these covert channels. Also, it is possible to have establish a covert channel between one processing unit to another processing unit when they don't have the possibility to communicate directly. So it is possible to go through the FPGAs by using the same modulations that I've already present, and we obtain the same transmission rate. So just one point between the different when we use bare metal or Linux systems. In fact, it is more easier to perform the covert channel with Linux, but the performance are lower. Just a use case of this covert channels. If you want to apply this to improve the remote side channel analysis performing inside the SoC. So in this case, is when a malicious entity would like to obtain informations when the victim applications execute cryptographic applications. So in this case, the malicious applications will perform the measurement and the analysis of the chat channel informations. So in most of the published papers, the physical channel uses the supply voltage fluctuations. So they need to be able to measure this fluctuation and also to have triggers for the alignment of the prior trace. So what we propose is to use the covert channel just to send one bit to say, as a trigger to say to the sensor, okay, it is the time when we have just asked for a ciphering, and so it will be easier to for the alignment of the trace at the end, because we know when the ciphers begin to execute, so to compute the data. So at the end, we have able to perform this side channel analysis inside the SoC without external triggers. So it is an improvement of the already work on this topic. Oh, sorry. So as presented this morning during the keynote, using maliciously change the frequency of a system on chip is a really serious threat for all the modern systems on chip, not only for fault injection, for side channel analysis, but also for the possibility to establish covert channels, communications inside the SoC. Okay, thank you very much for your attention. If you have some questions.
Any questions from audience? Okay, I will have first question. Hope audience can come up with more questions later. So my question is, so it seems like could be a really powerful attacks and affect a lot of SoCs in the future. So what do you think will be the perfect or immediate or rapid countermeasures to prevent such attacks happen more often?
Okay, in fact, the only strong countermeasure is like for the countermeasure against the COVID is to not share anything. Try to have a separate use of the resources in the system on chips, and so at the end to have a correctly separations between the clock domain inside the SoC. But in fact, it is in the opposite ways of the ways to improve the performance of the systems. So it is always a trade-off between the security and the performance, and so it's not easier to do it.
Thank you so much. Any other questions from the audience? Yeah, very interesting talk. I actually have plenty of questions, but let's audience ask first. Yes.
Think of the countermeasure against COVID, like having a little bit of a safety distance between the threads, between execution threads. It's not actually a bad idea, because typically you try to partition, but you have seen before that when you partition basically rigidly, clearly things do not interact. It's not quite true. They do interact still, but do not interact, and when you partition dynamically, clearly the cut of the partition depends on the work set size of the applications. So it would be interesting, as you said, that to introduce some kind of a coherency distance between threads that is really a property of the system rather than the application. And I don't want to say that's a direct mitigation to the end, but definitely would make the attack more difficult without compromising performance. Yeah. So that's an interesting thought that you had.
Yes. And moreover, perhaps the solutions is to have several programmable logic parts and to be able to dedicate it one part to the security, for example. So it is like an extension of the trust zones. Trust zone is only for the software's isolation of the processes. And for this kind of system on chips, it could be very interesting to have these extensions with several hardware parts. and correctly separate it, in fact, physically inside the socket.
Yeah. In fact, you have, partitioning in space, so to speak. You can also have partitioning in time by allocating slots and not leaving anything else in the middle. But clearly, none of the two things basically address the problem, how am I going to use shared resources effectively? All right? Is this interesting?
I will agree. Okay, thank you.
Thank you very much. Thank you very much. Very interesting work. Thank you. So the third paper, the presenter is Théophile Gousselot. It's a French PhD student at the EMSE Research Institution in the Department of Secure Architecture and Systems. His main research topic is the reliance of the RISC-V processors against fault injections. His work involves assessing the risk and the consequences of invasive attacks on processors, such as laser fault injection and the development of countermeasures. Théophile is a software and hardware engineer graduated from EMSE in 2021 with a master's degree in microelectronics. He worked on the control flow protection of RISC-V cores at ST Microelectronics prior to starting his PhD. Let's welcome our presenter. Thank you very much.
Thanks for the introduction. Hello, so my name is Théophile Gousselot. I am a PhD student at the Mines Saint-Étienne Institute. And today I will talk about linear code extraction attack. I will give firstly a background about this attack, and then I will continue with our contribution on this subject, which are the other thing of RISC-V vulnerabilities to linear code extraction, and I will introduce some lightweight countermeasures. So firstly, what is a linear code extraction attack? It's an invasive attack aiming at fully extracting a program from a memory. In some IP piracy context, it's very useful, for example, to build some counterfeit products like in cartridge. In that case, an attacker will try to extract code from an original in cartridge and will try to reproduce and imitate the communication functionalities of the original, on the original in cartridge into the counterfeit one. To carry out linear code extraction, it's necessary to perform microprobing. What is microprobing? It's the fact to electronically connecting a microprobe to an internal signal. For example, on these pictures, if the attacker wants to connect the signal in blue or purple to a microprobe, he will have to route it on the top layers of the chip and then to put in contact the microprobe. So this is a very costly and invasive attack, which involves tools like focus ion beam and scanning electron microscope. Let's see an example of, so linear code extraction involves microprobing. And to perform linear code extraction, the instruction bus must be microprobed. By this way, it's possible to eavesdrop the instruction traveling through the instruction bus. This allows to extract instruction. However, the instruction may be incomplete and out of order because only the executed instructions are extracted. To tackle that issue, it's necessary to microprobe other internal nodes of the core, but this time not to eavesdrop, to force some value to induce some linear execution. What is a linear execution? It's an execution when the program counter will point to every instruction one after the other in memory. In that case, the extraction will be complete and in order, and the reverse engineering of the code will be easier. Let's see an example now of a linear code extraction that we perform. So this is our target. And the first step is to identify some main components. For example, there is a memory and there is a core. Between them, there is an instruction bus. And if we follow this instruction bus, we can find an instruction register. There is also a program counter. So the first step of the attack consists to set microprobes on the instruction bus. And as we saw, the second set of the attack consists to put another set of microprobes to induce a linear execution. In that case, we decided to put the microprobe on the reset signal of the instruction register. By doing that, we hope that the instruction register will generate some NOP, no operation. So that means only NOP will be executed by the core, and in that case, the execution will be linear. So that means the program counter will point to every instruction in memory, one after the other. By this way, the eavesdropping microprobes on the instruction bus will be able to extract all instructions in the same order as they are in memory. Here is an overview of what we can get on the eavesdropping microprobes. So there are 2 bits of the instruction bus, and you can see that they vary from 0 to 1, depending on the current instruction in the instruction bus. So this is for the background. Let's now focus on our contributions. The first contribution was to assess the RISC-V core linear code extraction vulnerability and to define some main type. And for each of these main types, we evaluate the cost of the attack. Then we were looking to introduce some protection for these embedded cores, protection against linear code extraction, sorry. To help us on this task, we developed an experimental setup based on simulation framework. So that means we were able to execute some programs of the RM bench on our RISC-V core considered. We also developed a FPGA-based demonstration to perform linear code extraction in real time without the need to use the focus ion beam and semi-electron microscope. So let's now begin by the RISC-V vulnerabilities. If we consider again the attack, we saw that there are 2 types of microprobes. The first type of microprobe, the one to eavesdrop the instruction, must be on the instruction bus. So that means the instruction set used doesn't matter. So let's now focus only on the second set of instruction, the one to induce a linear execution. We define 3 types of attack paths to induce a linear execution. This is a view of a core with here the incoming instruction from the memory, there the program counter, and here an instruction register. The first type of attack path consists to freeze a continuity instruction in the instruction register. What is a continuity instruction? It's every instruction except jump, branch, and also discontinuity instruction. Let's see an example of what happened when we freeze a continuity instruction. This is a code in memory, and there you will see the executed instruction by the core, and here the extracted instruction by the eavesdropping microprobes. So let's begin the execution, and for example, we will decide to freeze the addition here. So from that point, the addition will be freezed in the instruction register. When the third instruction will be coming from the memory, the instruction will be extracted here. However, the addition will still be executed as it's frozen in the instruction register. If we continue the execution, we can see that only the addition is executed. In the meantime, all the instructions from the memory were extracted. So this is the first type of attack path. And what is interesting is it costs only 1 microprobe, for example, on the right enable of the register to be performed. The second type of attack path consists to edit the incoming instruction from the memory to turn every discontinuity instruction into continuity instruction. What is interesting here is that the microprobe to force the linear execution are on the instruction bus, which is the same place that the microprobe to eavesdrop. However, with the RISC-V instruction set without any extension, it costs 4 macroprobes to remove every discontinuity instruction without creating illegal instruction, and this is important. So the attack is more costly. Finally, the last type of attack path is to tamper with the program counter. For example, here, by forcing the value of the driving signal of the multiplexers, it's possible to select the second input, and by the way, to induce a linear execution. This attack costs at least 1 macroprobes, but the number of macroprobes can be improved or increased by enabling some other extension of the core. So all these attack paths were successfully performed on simulations, and thanks to our experimental setup. So now let's talk about the countermeasures that we introduced. If we consider again the attack, for example, by freezing a continuity instruction, in that case, an addition. It's obvious that any software countermeasures will not be able, is not viable, because the countermeasures by itself will be erased and replaced by the addition. So the countermeasures will not be executed. So that means a software countermeasures is not viable. It must be hardware assisted. Secondly, here the addition executed, it's a legal instruction. So that means there will be no exception raised from this execution. So it's not because you observe the executed instruction that you will detect the attack. So instead of that, we decided to monitor not the executed, but the unexecuted instruction. Let me show you our first countermeasures. We create a new instruction, a custom instruction called security marker. And we inserted in our design 2 little components. One just after the memory on the instruction bus. And this component will insert a security markers at a specific rate. On the core, there is another component. And this component monitors the execution of security markers. If an attack is performed, the security markers on the instruction bus will be replaced here by the addition, for example, and then the second component will raise an alarm because it will not see any execution of security markers. Let's see an example of what we can get on the eavesdropping microprobes, where a linear code extraction is performed without countermeasures on this line and with our countermeasures called security marker monitoring on the last line. As you can see, the beginning is equivalent. However, from that point, the attack were discovered and detected. And the component in the core reacts by giving an order to the memory to not send any new instruction. By this reaction, the attacker cannot extract the rest of the code. This reaction is just an example, and other reactions are available. For example, sending random instruction. In that case, the attacker will believe he succeeds the attack, even if it's just random instructions. So this is our first countermeasures, security marker monitoring, which consists to insert a custom instruction and to monitor its execution. Thanks. We introduced an enhanced version called discontinuity instruction monitoring. And this time, we consider on top that the discontinuity instruction are naturally present in the code as security markers. They are the same functionalities. And by this way, we will insert less security markers. This countermeasures has thus a lower clock cycle overhead. These two first countermeasures tackle the first and the second attack path and present a configurable latency, which depends on the rate of security marker insertion. Our last countermeasures, called linear addressing monitoring, consists to analyze the program counter update and to check if the program counter updates linearly for too long time. In that case, erase an alarm. These countermeasures tackle the 3 attack paths studied. We simulate and we implemented and simulate every of these countermeasures, and we succeed to detect the attack path. We also, thanks to our simulation framework, succeed to measure the overhead, clock cycle overhead, during execution without attack. So we get this graphic. So the DLT is just a term to say that one security marker is inserted every DLT instruction. So in that case, it's every 30 instruction. The average of clock cycle overhead is around 7% for the first countermeasures. For the second one, which considers the discontinuity instruction as security markers, the clock cycle overhead was measured below 1%. And here you can see the interest to consider the already in the code discontinuity instruction as security markers. For the last countermeasures, as there is no instruction inserted, there is no clock cycle overhead. On top of our simulation framework, we developed a FPGA-based demonstration, which allow to perform linear code extraction in real time by emulating the microprobing. So it's not necessary to use focus ion beam and semi-electron microscope to perform every linear code extraction. So by this way, it's possible to assess and observe the core behavior for different type of execution with the countermeasures, with freezing instruction attack path, for example. And this FPGA was performed with the Nexus Video and RTX7. By this way, we succeed to implement the 3 countermeasures and to detect the attack path. The area overhead was measured below 1% of the considered core. So to conclude, we highlight the RISC-V vulnerabilities to linear code extraction by defining 3 main types of attack paths, especially the freezing, which is easier to perform for the attacker. We introduced 3 lightweight countermeasures to strengthen core against linear code extraction, and they are enough lightweight for a mass deployment, for example, in cartridge devices. Finally, our experimental setup is open. It's available in GitHub, and it's composed of a simulation framework, which allow everybody to simulate any linear code extraction attack path. And if you want to perform your first linear code extraction, feel free to come at our hardware demo just downstairs. Thank you for your attention, and I'm ready to answer your question.
Give my first question, and hope give audience enough buffer time to think about more questions, if any. Very interesting work, by the way. Thanks so much. So my question was, so did you try to implement your attacks and the defense in different kind of hardware board, or do you think, wait, it doesn't really matter? This thing will be performed similarly in all kinds of RISC-V core-based hardware?
It's interesting question. The fact is, for the attack, the microprobes to heaviest drop are on the instruction bus, so it doesn't really depend on the core considered. For the second one, we can find the same type of attack path in every core. The difference is the cost for the attacker. For example, by another architecture design for these multiplexers, it's possible to increase the number of microprobes. So for the attack path, it's highly depending on the core considered. And for the countermeasures, they are, I think, very portable to every RISC-V cores and every cores, which it just consists to insert regularly security markers. And for the last countermeasures, it's just a monitoring countermeasures. It's just a passive solution. So in that case, it's compatible with every architectures.
other questions? Okay, I have another question. So it's great that your work is open source, so that everybody can give it a try, and even you also going to show the hardware demo in host. So did you try to also reach out to RISC-V community and see what they think about these attacks and countermeasures?
Not for now, but it's an interesting idea. I think it's for the attack and countermeasures, we use the RISC-V to build our demonstration, but it's more maybe a security topic, and it's not just limited to RISC-V. But yes, of course, it's interesting if there is some demonstrator with RISC-V to share it. Thanks.
Excellent. Thank you very much.
Thanks.
Thank you. Thank you so much. Thanks to our speakers again. Thank you. Great work. Thank you. Okay, our last talk for this session, Anthony Zgheib received an engineering master degree in microelectronics and computer science from EMSE School, France in 2019. He is a PhD candidate at the EMSE in the Secured Architectures and Systems Research Department, which is a part of a joint R&D team with the CEA, TEDI. His research interests are in the areas of control flow and programs execution verification, fault injection attacks, and RISC-V cores. Let's thank our speaker. Thank you very much.
Just presentation on Adobe, so it's better to open it from Adobe because. Okay. Thank you for the introduction. So my name is Anthony. I will present to you today our solution, CIFER. It's a solution that checks the code integrity and the control flow of programs that will be executed on a RISC-V core, while guaranteeing also its execution against fault injection attacks. So firstly, I will present a little bit of context about these attacks, which were introduced first by Bossuet in 1997. And I will present you an example. Let's say we have a processor, a RISC-V processor that is executing a program that will compare a user pin to the correct pins that it's already stored in its memory. So if you have these two pins that are different, usually in the normal behavior, you have that the user will not have access, so the authentication will be denied. However, injecting a fault on this operation could lead to skip or corrupt the condition or even the result of this operation. In this case, the attacker could have a notification granted based on the attacks that have been executed. So now if we look more in detail in the processor, so each processor is divided of pipeline of stages. So it has the instruction memory and the fetch stage and until the write-back stage. And there are protections that already exist that can protect the processor against the fault injection attacks, which are known as the control flow integrity verification schemes. And with these solutions, they can mostly detect the attacks on the first two stages of a pipeline. However, the state of the art of fault injection have shown that a fault injection attack could be made on any microarchitecture block of a processor. And most of the CFI solutions fail to catch this type of attacks because they don't have a visibility on the other blocks after the fetch stage. So this were required in order to protect, let's say, a program execution from the first stage to the last stage of the core. It requires to have a solution that really that follow an approach of a control flow and execution integrity CFEI. So in this talk, I will present to you CIFER, which is a CFEI solution. So it stands for Code Integrity and Control Flow Verification Scheme for programs executed on RISC-V core. It's composed of 3 steps, where will be detailed in this presentation. So the first one will be taking a RISC-V core. It will be the identification of the signals that are in its blocks or in all the pipelines in order to have a visibility of the instructions that will be executed, of what will be effect in terms of signals. And then for a dedicated program, we will generate metadata related to the signals in order to, that will be related to the correct behavior of this program. And the last step will be the verification of this metadata for the program with a dedicated hardware model for the CIFER. So here in the presentation, I will present you CIFER that is implemented on an IBEX core, which is a RISC-V core on two-stage pipeline. So if we go back to step 1, which is the identification of the control signals. So here I present you the IBEX core, which is with the two pipeline stages, the fetch stage and the decode stage. So to have a visibility on all the signals or the signals that are interested in order to take into consideration to the verification of CIFER, we evaluate and did simulations in order to have these control signals related to the instruction of the RISC-V or V32IM ISA, which are the instructions that can treat integers and also multiplication and division operations. And from our analysis, we have identified 22 control signals that could be target of fault injection attack in order to change the behavior of the execution of the program, which are represented also into 47 bits. So from our analysis, we can do a mapping, set the mapping between unique control signals values with any instructions that will be executed. And in this case, we will have, so with instruction, it's correct signals that need to be affected in the normal behavior. So here I will present you an example of the metadata that will be generated with the assembly code that is composed of 4 basic blocks, and each basic block contains instructions that are executed in order and consequently. So our program will parse the assembly code in order to extract the instructions. And from the instructions that we will generate, the control signals that are related to these instructions are represented on 47-bit. And then we will generate a signature of these control signals values based on the AMI-SR model. So now from our analysis, what will be stored in the metadata that will be reflecting the correct behavior of the program to be executed. So we present to you an example of metadata that will contain all discontinuity instructions of a program. And also it will contain the signatures of the basic blocks that each discontinuity instruction will point to. So we, for instance, if we take the instruction at the address 3A4, which is the branch not equal instruction, so in this case, we will have 2 signatures that will be stored also with this, with the branch. The first signature will be related to the basic blocks that will be correctly executed if the branch were taken, and the other one will be related to the basic block of the branch if not taken. So having these metadata that are related to this program, how, while execution, a program could be verified. So here I present to you the step 3, where the CIFER metadata are verified. So in order to have also on runtime the information about the program that is executed on the RISC-V core, we implemented the AMI-SR model, which will generate the CIFER signature while reading the internal signals from connected to internal signals of RISC-V core. So here there will be the signature will be calculated. And then using a RISC-V model, which is a trace encoder, we will send this signature with other information in form of packet to our solution, the trace verifier, which will check the information of the content of this packet to the metadata that have been generated, and I present you an example of the previous slide, contained in its memory that have been generated from our static analysis program. And then the trace verifier will check the coherence between the send packet and also the metadata that are stored in its memory in order to say that if a fault injection attack have been executed or not by raising an alert signal. So this solution, it's a co-design one. Mostly it has an impact on the hardware aspect because in software we don't touch to the user code nor the RISC-V compiler. And the hardware part we implemented so the MESR module and also our trace verifier and memory to contain the metadata. So now I'll speak a little bit more about the trace encoder, which is usually, so mainly developed by RISC-V for debug purposes. But in our case, we will use it for CIFER verification. So the trace encoder compresses at runtime sequence of discontinuity instructions that have been executed by the RISC-V, and it will also send in form of trace packets information about the execution flow of the program. And these packets are sent according to the trace encoder standard. In our case, and to be able to do CIFER verification, we did an enhancement to the trace encoder standard in a way to send a packet after each discontinuity instructions that have been executed. In this way, we can have a quick verification of the basic blocks that have been executed, and we can detect if there are an alternation in its control signals. And also the other improvements or the enhancements that we did is we added to the trace encoder content the signature of these signals. So here I present you the difference or the packet content of the trace encoder packet when to the right where it respects the norm and to the left where the packet content is sent while we are working in a CIFER verification. So we can see that we also add a signature on 47 bits. So having this packet, how our trace verifier work. So the verification process starts when the packet is received. So here we present you the architecture of the trace verifier. So when a packet is sent, it will be stored in a FIFO module. Then our final state machine will read it in order to, in the third step, extract the content of a packet, which are, for example, here, the address and the signature of a basic block that have been just executed. Then, in the fourth step, the trace verifier will navigate through its metadata in order to extract the information about this basic block that, in case of a correct execution, we will have the compatible and coherence between what is sent with the packet and also with our metadata. So here in this case, we will, this packet is sent after executing a jump instruction to the address 3BC. At the index 42 of our metadata, we can check that at the instruction, from the instruction we can extract the jump address, and also we can extract the basic block signature of the control signals that are related to this basic block. And the last step will be the comparison between the content in order to check the coherence. So here I present to you a simulated fault injection attack on a branch instruction control signals in order to speak a little bit about the covered threads with our solution. So let's say we have the instruction at the address 3A4, which is a branch if not equal instruction. So let's say, for instance, that it's correctly fetched, and now we arrive to the decode stage, where this instruction will be decoded into different signals and various signals. So mainly in the correct behavior, we have in signals that will communicate with the early operator in order to compare, here in this case, A4 to A5, and to take a decision if we need to take the branch need to be taken or not. So we expect that the operation of the ALU is equal to not equal test. However, an attacker could inject a fault to the signal in order to change the operation of the ALU from testing the non-equality to an equality. And in this case, we can have a skipping or if we can corrupt branch instruction, even though that from a software way, we can see that, okay, the branch not equal instruction is correctly executed, but in the microarchitecture, what is correctly executed in a branch if equal instruction. So this is a simulated fault injection attack. However, in reality, it's a little bit complex, but it's feasible. So while the MESR module is connected to the core, we can detect, or while computing the signature, the ALU operator also is included in the signature, or the signals that have been generated or chosen to calculate the signature. So the signatures that will be calculated will be different from the ones that will be expecting it. So at the end of the execution of the basic block, there will be a packet that will be sent from the trace encoder. And so here I present you a simulation of the verification of this packet. So firstly, once trace verifier will receive it, we will, as I mentioned before, there will be the steps required in order to be able to verify the coherence between the metadata and also the program followed path. So after the fifth step, there will be an error flag that will be raised because the signatures are not compatible, and you can detect that an error have been, or a fault injection attack have been introduced to control signals of the basic block that is studying here. So now I will speak about the solution matrix. So we tested our solution with different benchmark from mBench IoT, Polpino project, and other that are classical one, and we compile it into different compilation level, 01, 02, or 03. And here I present to you the ratio between the metadata and the code size, which is ranged from 16 to 68%. However, the metadata size will really depend on the application and how many discontinuity instructions are contained in the program. So speaking about the hardware overhead, so as I said, we implemented CIFER on the IBEX core. So the core, it requires 645 slices, and we had additionally added 25 slices were being added to in order to connect the signals of its pipeline to the MESR model. The trace encoder by default requires 239 slices, and we had 46 for the enhancement for sending a packet after each discontinuity instruction, and to contain also the signature of the control signals. And so the MESR model requires 58, and the trace verifier required 183 slices. So in overall, our trace verifier represents 35.2% in terms of slices with respect to the unmodified trace encoder and also IBEX score. So I arrive to the conclusion and perspective. So I present to you our solution CIFER with verified programs, control flow and execution integrity, CFEI, that is running on an IBEX core. And with this solution, we can detect fault injection attack on any instruction of the RV32IM RISC-V ISA extension, and also related to the control signals of these instructions. For the characteristic, we have no software performance penalty. We don't change the execution time of the program that is executed. And we don't also have modification to the RISC-V compiler or the user code. However, CIFER could be adapted to other RISC-V cores by having really a deep knowledge of the microarchitecture in order to extract the signals that are really interested to be protected against fault injection attack, and to have also the correct length of the signature. So CIFER, in order to be, it's based on the trace encoder, but it's not the trace encoder forming the norm. In order to be able to implement it, also we need to do an enhancement to the trace encoder standard. For the perspective for our solution, we also want to check how indirect cores could be treated, because indirect cores, we don't know from static and from the static code, the jump addresses, which is a little bit complex in order to be able to generate metadata to be verified. And then we want to work with the CIFER on the IBEX core by having the branch prediction feature enabled. And at the end, upgrade CIFER to handle interruptions and core exceptions. From here, I arrive to the end. Thank you for your attention. I'm willing to answer your questions.
Rob Aiken, Synopsis. This is more of a curiosity question. So you mentioned briefly when you put up your picture that showed the fault attack, that the specific fault attack you were looking at on that arithmetic operation was challenging to mount. What did you mean by that? How challenging?
So, yeah. So as I mentioned, it's done on while simulation. So simulation we can do
Whatever you want. Yep.
Yeah, exactly. So in reality, we're specifying and how do you know specifying attack on a single or let's say a signal. It's really complex to do it. So this work is not done yet, or let's say in physical, but it's possible, but it's complex, yeah, to be able to really target a specific signal of the architecture.
Okay, and from your perspective, you don't really care because you can detect it anyway, right? So.
Yeah, but so I didn't mention here, but this is the assembly code of the verify pin. So with this skip, we can also skip the verification of the pin code. So so it depends really on the purpose of the attacker. But in all cases, if an attack have been done on other signals, also it will be detected, but maybe it will not give him access or an authorization granted. So it depends really on what's the purpose of the attacker.
Okay, thank you.
Yeah, you're welcome.
Any other questions? I have a question about the benchmark. So do you have any estimate, like size or scalability of the benchmark you have been running for this work?
In our cases, we didn't have a limitation for it. So we had just limitation for the benchmarks that contain indirect jumps that could not be treated. But for the length of the benchmark, it doesn't matter for us. So we can, it will just maybe have, we'll have more packets to be treated. Yeah.
Thank you very much.
Yeah, thank you.
Let's thank our speaker again. Thank you. Thanks so much. Okay. So I think this is the end of the session 6. I think the next session